Okay, so why don't we get started? Why don't I start first with a land acknowledgement and then we'll do the introductions. So I've been using this land acknowledgement that the students in the PCC communication seminar fall quarter created, and I think it's really great for our seminar as well. So I've been using this every week. As we begin our gathering, we respectfully acknowledge that our event today is taking place on occupied Coast Salish land and that the University of Washington is on the homelands of the Duwamish people. We pay respect to Coast Salish elders past and present and extend that respect to their descendants and to all Indigenous people. To acknowledge this land is to recognize its longer history and our place in that history. It is to recognize these lands and waters and their significance for the peoples who lived and continue to live in this region, whose practices and spiritualities were and are tied to the land and the water, and whose lives continue to enrich and develop in relationship to the land, waters, and other inhabitants today. So I'll turn it over to the introducer.
Thank you. So for this week's lecture on heat waves and health, we have Dr. Nicholas Bond and Dr. June Spector. Dr. Nicholas Bond is current Washington State climatologist. He's currently principal research scientist at the Cooperative Institute for Climate, Ocean, and Ecosystem Studies. Dr. Bond received his PhD in atmospheric sciences from the University of Washington and his bachelor's in physics from UC Riverside. A majority of his current research is under the broad umbrella of the fisheries oceanography coordinated investigation, and much of this work has been on the variability in climate and atmospheric forcing of the Bering Sea and topographical effects on coastal winds in Alaska. Next will be Dr. June Spector, who's associate professor and assistant chair for the Department of Environmental and Occupational Health Sciences. She received her MD from Yale University, her Master of Public Health from Johns Hopkins University, and bachelor's from Harvard University. She's currently UW Director of Occupational and Environmental Medicine and Deputy Director of the Northwest Center for Occupational Health and Safety. Dr. Spector is a physician scientist with a focus on the prevention and management of adverse health outcomes related to heat exposure and other climate-related hazards in working populations. She is actively engaged in interdisciplinary research to evaluate health benefits of conservation interventions to inform progress towards sustainable development and climate goals. Her research goal is to equitably and sustainably assess and enhance resilience to human health effects of climate-related hazards, including heat and wildfires. Really excited that these two are here with us today. They can take the floor now.
Okay, June, I think you can go ahead and share your screen.
Great, I'll do that. Thanks for the introduction. Okay, can you see that okay? Yep. Okay, sounds good. All right, great. Well, it's great to be here and it's great to see all of you. What I was hoping to talk about today was some of the challenges we've been struggling with in investigations of outdoor working population adaptations to heat. So what I'm hoping to do in the about 20 minutes here is to divide this up into about 3 sections. So first, I'd like to briefly talk about the process of defining an actionable question in this space. And then secondly, go through a framework for thinking about methodological challenges we face, for which it's important to have a well-defined question. And then finally, go through an example. So one question that often comes up from various folks, including practitioners and stakeholders and others, is what heat adaptation approaches should we invest in for outdoor working populations? However, of course, this question is extremely broad, and to move forward, we then need to figure out what health outcomes we're talking about and what populations, locations, and time period. So as you know, there's a number of different health outcomes that are associated with working in hot and weather. And these include, of course, heat-related illness, and we'll define heat exposure and outcomes on the next slide, but include things like heat stroke and heat exhaustion. Oops, sorry about that. Heat has also been linked to traumatic injuries in several studies, including epidemiological studies conducted here in Washington State in outdoor populations, including agriculture and construction. The proposed mechanism for that includes heat's effect on cognition, fatigue, and balance with dehydration, for example, during work from heights, which could be related to falls and injuries. And then heat is also associated in some studies with acute kidney injury across growing seasons in agricultural workers, for example, in California, and is hypothesized to contribute to an epidemic of chronic kidney disease, originally described in sugarcane workers in Central America, and now also seen in other parts of the world. Heat can influence pregnancy and birth outcomes. And in studies that for the most part have assumed that working populations have worked within health and safety guidelines, which we'll talk about later, for example, under certain exposure thresholds, there have been described extreme productivity and economic implications of heat in the future. So you can see there's a very broad array of health effects here, but to develop a good question, I think we need to be clear on what outcomes we're focusing on. So for the purposes of thinking about this question, we'll focus on the heat-related illnesses. So let's step back for just a minute and define terms. Unlike for the general population, for which most people hear about classic heat stroke in the very young and elderly, occupational, sports, and other exertional contexts include several inputs into the exposure of heat stress. So that includes environmental heat exposure, but also metabolic or internally generated heat from heavy physical work. Turns out that human bodies are not very efficient, and so we actually generate heat when we work. And together this is referred to for our purposes as heat stress. And then when the body's natural physiological response to maintain normal core body temperature or heat strain is overwhelmed, we can develop the heat-related illnesses we mentioned before, which in contexts where people are exerting themselves is referred to as exertional heat stroke. And this can be fatal if not immediately addressed. And then there's a number of less severe heat-related illnesses as well. So having defined outcomes of interest, then another key question is the population and geographic location to focus on here. So we can look to surveillance data to help with that. For example, these data from the US Bureau of Labor Statistics to identify industries and working populations at highest risk, which include agriculture, as you can see, which had a very high rate ratio compared to all other industries of heat-related deaths from 2000 to 2010. So we may refine our question then to state more specifically what heat adaptation approaches should we invest in for outdoor working populations, focusing on occupational heat-related illnesses, so those related to work. And in terms of the population, location, and time, focusing on US agricultural workers, and then we have to think about the time period, so say by the end of the century. To begin to answer this question, which we will definitely not answer in this talk, rather I want to kind of just use this to bring up the challenges in starting to think about addressing questions like this. We definitely need an interdisciplinary approach, I think, that combines climate science, physiology, epidemiology, occupational health, and other disciplines. So one of the main challenges in both understanding the health impacts of heat and also evaluating potential adaptation approaches over time is uncertainty in projecting these heat health outcomes. And so I'm borrowing a schematic that was developed by Jenny Vanos and Chris Ebi that qualitatively illustrates contributions of uncertainty in different areas over time, as represented by the colored bands. So in addition to approaches to address uncertainties in future emissions, the natural variation of the climate system and structural uncertainty, which are in gray and I'm not going to talk about. The paper basically talks about how we need to also think about approaches to address uncertainty in bioclimate model structure, in purple, population diversity, in orange, and adaptive capacity in green. So if the variability in these factors is not captured in present day studies, so say epidemiologic studies, looking at the relationship between exposures of heat exposures and health, then it's very difficult then to have a basis upon which to project health effects. And we need to develop better methods to take into account uncertainty in the effects of these factors, as well as their potential changes over time. And so I'll go through each of these three on the next few slides. So starting with population diversity, this is socio-demographics and other factors specific to working populations for the questions we're talking about today. And I'll talk about these next. So you've seen this figure before. Basically, there's individual and workplace factors here in red, including things like clothing. So wearing non-breathable clothing that inhibits evaporative heat loss. So humans tend to lose heat mostly by evaporative heat loss through sweat. And acclimatization, which can occur over 4 to 14 days, ideally with gradual increases in the amount of time working or exerting yourself in hot conditions, but it can be lost in as quickly as 2 days. These things can influence the development of heat strain given heat stress or of heat-related illnesses given heat strain. And so one key note is that some factors may not vary over a working lifetime, but other factors such as workplace factors, so for example, changes in tasks and work environment, they may vary on an hourly or sub-hourly timescale. So daily data will not be sufficient to capture this variability. In addition to clothing and acclimatization mentioned on the last slide, there are additional workplace factors, such as those that we've identified in the survey of Washington agricultural workers, to be associated with symptoms of heat-related illness. So for example, being paid by the piece, or that means basically by the amount harvested, rather than working hourly, or needing to walk a far distance to get to the toilet, with the rationale being workers are less likely to hydrate if they need to stop to use the restroom, especially if they're being paid by the piece. These are factors that have been investigated in this and other studies. We, of course, have personal factors as well that influence the risk of developing heat-related illnesses. Here, taken from a heat risk self-assessment that we use for educational purposes, including health conditions, medications, or drugs that affect metabolism, sweating and evaporative heat loss, and fluid balance, and certain behavioral factors. So that was population diversity. Now I'm going to talk a bit about this idea of bioclimate model structure. So these models aim to predict aspects of human thermal comfort, stress, or strain through integrating weather variables with human factors, so things like activity and clothing that we talked about before. So it turns out there are multiple, more than 160 thermal metrics out there, and different approaches, and this is sort of crudely categorized, but from simple to complex. So simple metrics are often used and are computationally easier, of course. They're easier to forecast and have public communication advantages. So an example is the heat index. And on the right there, you see a figure showing different health risk categories for workers. And then there's those that are more complex and integrate environmental conditions, human physiology, and behavioral aspects, and are typically better predictors of health outcomes. So it turns out that different metrics and approaches may provide very different outcomes that are dependent on how and why the given index was created, as well as its application. So an example of an approach that falls somewhat between simple and complex in its application, which I'll talk about in a minute, is a wet bulb globe temperature. So this was originally developed to manage heat illness during military training in hot and humid environments. And characterized in this particular framework from the paper that I mentioned, it's characterized as a simple index on its own. It does capture drier temperature, humidity, wind speed to some extent, and solar radiation, unlike the heat index, which is a function of temperature and humidity, doesn't take into account directly solar radiation or variability in wind speed. And although these simple metrics have typically been used in projection studies, heat thresholds that are just solely based on heat index or wet bulb globe temperature alone don't fully take into account other factors that affect human heat balance, including, again, things like activity and clothing, personal factors. However, these other factors are taken into account to some extent when these metrics are applied in a framework or integrated, for example, into occupational health and safety guidelines, such as those from the American Conference of Governmental and Industrial Hygienists, or ACGIH, and there's other examples as well. This is kind of a busy slide, but for a moment, if you'll focus on the red things, based on human studies in controlled conditions, ACGIH, for example, has developed adjustments to wet bulb globe temperature risk categories based on things like work rest cycles, metabolic rate relevant to internal heat generation related to exertion, and clothing, as shown in red. to highlight an example of this, because I think it's a little bit hard to sort of read the whole slide. So for example, workers doing moderate metabolic rate work, so that's 300 watts, with 70 to 100% allocation of work in a work cycle, or a cycle of work and recovery, it is recommended that the wet bulb globe temperature not exceed 28, assuming they're wearing regular work clothes. But depending on the clothing worn, for example, if non-breathable clothes, you can see that that would adjust the threshold down. The duration of exposure is, of course, important and partly captured in the work rest cycles, and time-weighted averages are recommended if exposures vary over the course of a workday. So here's an example of this method applied to a group of 46 Washington apple and pear harvesters from 6 orchards that we collected over a work shift in 2015. And you can see that in this, of course, very small sample over just one work shift, about 44% exceeded the threshold limit value. And then we used ingestible core body temperature sensors and chest band heart rate monitors to determine whether folks met definitions for heat strain. You can see about half exhibited some level of heat strain during the shift during August pear harvest. And I will say that we identified a lot of different microclimates in these large fields and orchard blocks. And so we use this handheld digital wet bulb globe temperature meter near workers as we were doing measurements. And so note that the threshold and results would have been different for a different group of workers doing different intensity tasks or wearing different clothing. And even with those factors constant, as in this group, there were differing physiological responses to similar environmental conditions driven by the factors we covered earlier when we talked about population diversity. So I want to move now to the third category here, which is adaptive capacity. So in a workplace setting, there's a number of farm level adaptations that are currently recommended, including engineering controls of shade and cooling, various administrative controls related to hydration, restroom locations, work shift timing, and personal protective equipment or clothing, for which there is, of course, variability in practice currently and will be in the future. And there are other uncertainties in future labor force, agricultural processes, for example, mechanization, which we definitely see here in tree fruit in Washington State, and community cooling opportunities. And it is, of course, problematic to apply the current literature, which focuses mostly on developed and urban areas in the general population and future projections of rural populations. So that leads to the example. How can we begin to understand some of these uncertainties as we ask what heat adaptation approaches should we invest in for outdoor working populations? So I wanted to share with you the results of a study that was led by Michelle Teichelaar, who's a former UW Atmospheric Sciences postdoc, who's now at Stanford. And here we focused on the contiguous US to calculate increases in heat health risk for agricultural workers with 2 and 4 degrees Celsius of warming. However, what I think is most germane to this conversation is we also tried to quantify the effects of various workplace adaptations on mitigating this increased risk. So here we show present day and projected 2 and 4 degrees Celsius warmer world agricultural worker exposures. So on the left, you see the number of days, and on the right, the number of worker days to heat above occupational health guidelines. So this was using the ACGIH method, which I will caution and say is really, though developed in laboratory studies, it's really intended for situations where you actually can make observations in workers. So it's a bit of a stretch here. So for the baseline scenario, we assumed that all workers are acclimatized and performing work activities in a 90% work rest cycle at a moderate metabolic rate. They're spending breaks in the shade and wearing double layer protective clothing. Here we show the effect of different combinations of adaptations at present on the median number of days per summer with daily mean temperature exposures greater than the threshold limit value at present, and then with 2 and 4 degrees Celsius of warming. And so here you can see that just resting in air conditioning, which is sort of the middle red highlight, doesn't really improve heat relevant exposures much below baseline, which is at the top. But combinations that include reducing time worked per hour and changing work pace, so changing it down, may be more effective. However, changes in effort and pace could affect farm productivity, farm worker earnings, and or labor costs much more than alternative measures. So that suggests that safeguarding the health and well-being of US crop workers therefore will require systemic changes beyond the worker and the workplace level. So note that here, though we vary the adaptations, and you can see how much of a difference it makes when you do that, we did not vary them over time. We did not address population diversity, so we didn't assume changes in the population over time. We didn't use more complex bioclimate models. So to me, this sort of illustrates the challenges here and the amount of work that there still is to be done to really understand these issues. So in conclusion, I think there are several fundamental methodological challenges here that still haven't been addressed, but that are needed in order to tackle some of the questions that we talked about today. We need a better understanding of uncertainty and adaptive capacity, population diversity, and bioclimate model structures. And one of the things that's brought up in Chris's paper is, should we develop a standardized ensemble or group of pathways that incorporates differing physiology, behavior, clothing, et cetera, to inform our understanding of heat health risks and to inform adaptation strategies. And so maybe that's something we can discuss in the breakout. But I think the other key thing that I wanted to get across here is that working populations, and that is a very broad term, there are many different types of work, obviously, but I think they have special considerations that differ from the general population and that are not addressed by a one-size-fits-all approach. And so some of the points that I hope came across are the timescales for exposure, activity, clothing, behavior, and settings, for example, rural settings for agriculture, that may be less studied. So I'll go ahead and stop there.
Okay, so why don't we pass it on to Nick and hold the questions until after Nick is done. Go ahead, Nick, take it away.
Yeah, thank you.
And chat is open for, I think Nick is going to have some interactive stuff. So the chat is open if you want to respond.
Yeah, so what you should be seeing here on my screen, hopefully, give it a sec, is a cartoon from the Salt Lake City Tribune, August 2015. Everybody see that? Okay, yeah, I've gotten a lot of mileage out of this cartoon, and I'm bringing up 2015. You'll see as an example to kind of show why some of the issues that Dr. Spector was just talking about are already present and something we have to deal with. And what I like about this cartoon, it's suggesting all these things that are happening in the US West and how it might be linked to climate change, and that it also was published in a newspaper from that hotbed of environmental activism known as the state of Utah. But anyway, so today I'm going to kind of flit around between showing some historical observations, some climate change projections related to heat waves, and a little bit how this, the human health linkages. All right, let's go back to 2015. It may be kind of hard to believe considering all the snow that's fallen in the Cascades in the last couple of weeks and that sort of, but about that time of year, 6 years ago, this is what it looked like at Snoqualmie Pass. It was a real wake-up call for the climate community. That was also the year that some extraordinarily warm ocean waters developed off the west coast of North America, affectionately known as the blob, right? What happened that year from in terms of surface temperatures from for the annual average temperatures, January through December? These regions in red show where it was the warmest year of all time, going back to the 1890s. For the state as a whole, it was comfortably the warmest year on record, almost 4 degrees Fahrenheit greater than the 20th century average, which is a big anomaly. And even those places that weren't the record were up in the top 10%. If we focus down on the warmest time of year, and in this particular year, what was really extraordinary was June and July. Again, records set all over the place with the temperatures for that 2-month period over 6 degrees above the average, which is, again, an extraordinary amount. So what did that mean in terms of this parameter that was introduced just a few minutes ago, the wet bulb globe temperatures around here? And again, this is a kind of moderate complexity, but does take into account some of the factors that actually contribute to heat, strain, and stress, and so forth. And towards that end, I want to look at the specific example of what happened at the end of June during that year. What this is a map. You might hopefully recognize some of these city names: Walla Walla in the lower right corner, Cle there toward the upper left. And at 4 p.m. in the afternoon, these are the actual temperatures that were being reported at various stations around here in the Yakima Valley, Lower Columbia Basin, and some fairly hefty amounts, you might say. Look at it here, 113 Fahrenheit, 111, plenty of, mostly over 100 degrees Fahrenheit. And so very, very warm. Our warmest months in the Pacific Northwest are July and August. And so to get this kind of heat in June was really something. Along with that was something that the wet bulb globe temperature takes into account, the humidity. And there were actually relatively high humidity conditions reported in some parts of eastern Washington. And so those higher humidities are in orange here, and you can see here in the Yakima Valley and in the irrigated portions of the lower elevation of the Columbia Basin, that's where the dew points were higher. That's where the humidity was higher. And it's in large part, because there's more irrigation there. And this is where the agricultural workers are that are exposed to, this kind of conditions. There's actually a handy little widget application that was developed by the National Weather Service, so you can put in some values and see what that wet bulb globe temperature was. Here for that day of June 28, 2015, I put in some representative values. This 105 isn't actually the hottest temperature, and some of the one of the maybe lower dew points, 53, and you get a wet bulb globe temperature 85, which is just under 28, which is I'm sorry, this is just under 30 degrees C, and so this is getting way up there. If you look at what the wet bulb globe temperature was in some of the more humid places, again with conditions representative of what happened for a couple of days there, you get wet bulb globe temperatures of something like 90 Fahrenheit. And when you talk about what that means for folks that are exposed to that and doing anything from light to moderate or even greater amounts of activity, that 85 here is in the category between moderate and high. That 90 is where you go from high to extreme. And the idea there is with moderate work, even if you're acclimated, you can't really work more than maybe a third of the time or so. And it's hard to believe that agricultural workers would be let's say, encouraged to have that much downtime in those sort of conditions when that is a time when they have to be active. Okay, so like I warned, I'm going to be flitting around a little bit. Here, what does climate change portend for us? Using an ensemble of climate models and a rather kind of on the extreme side of where greenhouse gas emissions are going to go and temperature rises and so forth. What these maps show is for winter on top and summer at the bottom, and focus here on temperature on the left, is what the expected change is for these models as a whole for the kind of middle part of this century, 2040 to 2069 to be specific, relative to the basically the end of the 20th century. And so what the models are suggesting in summer is an increase in the mean of something like 3+ degrees C. If you back to that example I gave of what happened in 2015, during June and July of that year, the temperatures were about that much above normal. And so what we're saying is that what happened in that extreme year in the recent past is going to be more what's going to be the typical year in the future if the models are on track and if we continue doing what we're doing as a globe in terms of greenhouse gas emissions and so forth. All right. So as threatened, here's I got a question for you guys now. Do you think that the daytime or nighttime temperatures are actually warming up so far here in faster in Washington State? So you can, I don't care if you enter it in the chat or not, or you can just think about it to your on your own, but I'm going to give you just a second to do that. And that's all, time's up. Let's look. And so here, what I'm doing for the months of June through August for the state as a whole, we have records going back to the 1890s. This shows what the mean maximum temperatures are each year back to 1895 through 2020, that 3-month average. And you can see there are kind of cooler periods, warmer years, a general upward trend. Okay, but a lot of noise in that signal. Compare that with, and these are the maximum temperatures, daytime temperatures. Compare that with the nighttime temperatures. Much more of a systematic increase. There's less year-to-year and multi-year variability, and just a bigger systematic rise there. But I'm going to kind of come full circle here. That doesn't mean that necessarily it's going to be a bowl of sugar pops for folks that have to work outside, in that our records don't go back as far, but the humidity is going up also. And an example that I presented there, a big impact on the heat stress for people outside is just how humid it is and how effective you can perspire to cool off. And what we're seeing in terms of the absolute humidity values in, again, this is for the Washington State as a whole, and kind of low levels, the lower couple of thousand feet, can see a systematic increase over the last 70 years or so. While, in this kind of two-part lecture, we're a little bit of a focus on the outdoor working community. There's also other groups that, of course, are impacted by heat waves. And in particular, it turns out that folks, seniors who are stuck in kind of apartments without air conditioning and so forth, that it is the nighttime temperatures that are really can be a problem. That if you can't dump the heat, relieve the thermal stresses you've accumulated during the day at night, then after a couple of days, it can be some real problems. And one of your lecturers, I forget whether she already had a lecture or has one coming up, but Tanya Bush-Isaacson has shown that this measure that includes both temperature and humidity, that here right in King County, that we really see the impacts on just emergency room admissions when both the heat and the humidity goes up. Another thing that I'm not going to belabor this at all, but there's always Other factors, it turns out when it's hotter here, certain aspects of the air quality are worse also. And in particular, ozone concentrations are, and this is an example from the hot summer of 2009, are very much linked to the temperatures around Puget Sound. Turns out that it's the pollution from the populated areas of Puget Sound, it doesn't directly cause ozone. It causes the precursor conditions that during hot and sunny conditions then turn into ozone. With the winds generally from west to east, that ozone blows into the foothills of the Cascades. And so it's communities like Enumclaw and North Bend, high ozone values. But there's a confounding factor, certainly. The idea that heat waves are in the increase, especially these nighttime ones, is kind of borne out by this sort of perplexing, probably image from a paper published some time ago. These red and blue dots show the kind of hot day type heat waves and in red, and the blue circles are the hot night type ones, with the size of the circle proportional to the magnitude. And the point here is that there's been these hot day heat waves through the, plenty in the past decades. Plenty recently, plenty in the past, but there seems to be more and more of these hot night ones in recent decades. And some work the Climate Office has done has kind of borne that out here in the Pacific Northwest also. Some other information about how temperatures are trending. These are actually in the observations. These series of maps show for the US, of course, for different periods. This is the left column is for 1900 through 2011. And the middle column is kind of the last 60 years considered. And then this last one is the last 30 years or so. And the three different rows are different ways of kind of putting together that data, and different adjustments that have been used for changes in instrumentation, sighting, and so forth. But the screaming message is, especially when you're looking at recent decades, that the trends in summer maximum temperatures are definitely up, but it's not one size fits all, in that there are some places just probably more, in part a fluke, in part it can be land use practices and so forth, just haven't had the same amount of warming. Another way to look at that is to just look each year at the proportion of maximum temperature, daily maximum temperature record set versus minimum temperature record set. And this takes into account changes in the density of the observations and so forth, and can see just over time that the red dots, this east left column is for the eastern US, the right column is for the western US. There's more and more of these kind of T-max records shown with the red dots, and the T-min records shown in the blue dots. And one thing that's kind of interesting here, that just as kind of an aside, is what we can see here is there was actually a dip in that ratio between the T-max records and T-min ratios for a couple of decades here, because of the effects of pollution, basically. More aerosols in the atmosphere are kind of scattering away the solar radiation. But as we kind of cleaned up our act here a few decades ago, or to an extent at least, that effect was no longer evident. Another way to look at this is from an EPA publication. Again, just looking at the percentage of the land area, this is for the US, experiencing these hot daily, the daytime heat waves and nighttime heat waves. You can see that recent 30 years, more of that area has been experiencing that, and that increase has been especially in these the kind of hot nights, you know, in the summertime. But again, from a physiological point of view, this is associated with an increase in humidity, and so that's no bargain if you're working outside. Perhaps you've seen something like this, but while heat waves don't necessarily seem as high on the Richter scale of meteorological phenomenon as some things, by some estimates, they're actually the biggest source of mortality due to weather events. And here, what's kind of hard to separate is there's usually comorbidities that people have, you know, health problems anyway. But anyway, the way it's estimated, and this, to be sure, is not just outdoor workers, but especially those less able to cope with the heat, seniors, infants, and so forth, that though heat waves may be the biggest killer. I can't stop myself from talking a little bit about the ocean, and this is not just in deference to your Professor Luann Thompson and so forth, but just to point out the ocean is soaking up a lot of the extra heat in the whole climate system. And we can see that in sea surface temperatures off our coast. Here's a box about 1,000 kilometers on a side off our coast. We have reasonable estimates based compared to a baseline value going back to about the turn of the 1900 or so, and temperatures kind of go up and down year to year variations. There was kind of the precursor to the blob here in 1958 that actually was a really warm, humid summer in the Pacific Northwest. And so it's going up, and then, whoa, check your socks. Look what happened in 2015. This is what stunned the real wake-up call for the climate community. And we didn't think something like that would happen for a few decades. And getting to the idea that marine heat waves matter, they are associated with definitely a human health issue, and that is harmful algal blooms here in the waters of the Pacific Northwest. And so the one that occurred in 2015 was unprecedented in its geographic scale and duration and so forth. And just want to say that it's not just atmospheric heat waves, but marine heat waves that are threats to humans. And I'm not sure how what the actual health impacts were of this, but certainly the Department of Health in all the states along the West Coast and so forth shut down recreational and commercial fisheries in recognition of it. But not always does everyone get the memo. So again, I just don't know what the actual consequences were. I'm going to just skip a little bit here. And I want to get to a discussion, but say, climate change is real. Well, we just had a big cold event in Texas, and everybody's still, thawing out from that. But it is a real thing, and we're still going to have weather variability and so forth, but that doesn't mean it's not happening. And people can always find time series that seem to kind of refute the idea that it's happening. And here, just a local example, Odessa, Washington, in the Columbia Basin. If you just plot the number of 100-degree days it's had there over the instrumental record, what's there to get excited about? It was a lot hotter, or a lot more hot days back in the late 50s into the 70s. And there you have to be careful, amongst other things. Land use practices could be a lot of it. The irrigation in this district really kicked in kind of the late 70s and so forth. And so now those fields are being watered, and the energy from the sun is going into evaporating that moisture and making it more humid. And so maybe it's not as hot, but that again doesn't mean that there's not less heat stress on the folks that have to be outside. So again, there's always going to be people, you know, doubting whether we have to worry about it or not, but you know, it's real. And in particular, what's relevant to what we're talking about today is that, and I'm apologize if you've already been introduced to the idea of, you know, how the climate is shifting, but I think this this kind of figure that shows the maybe the historical distribution of temperatures here in gray versus the expected um, future distribution of temperatures really kind of shows that it's not so much, you know, the changes in the mean that are necessarily going to be a big deal, but it's the changes in the extreme. And if you say, well, at these kind of temperatures, this is when we're starting to have impacts on human and natural systems and so forth, that because of this shift in the distribution, even if the shape doesn't change, there's got to be a lot more of those events. And then you're going to have the chance for having these events that are just unprecedented, you hadn't seen before. So especially when you get out in the extremes, suddenly it's a lot more likely to happen. And this is just, again, assuming just this, the shape doesn't change any, but the just that shift in temperatures. Again, you know, at the risk of belaboring the obvious, is, you know, we have a climate and we have health outcomes, but getting back to what Dr. Spector was talking about, you know, we can do something about that. Obviously from, and I gave some examples that probably are happening in Eastern Washington where land use changes impact things, you know, positively, maybe negatively. But then also we have a chance to do something about it for the folks that are more vulnerable or exposed to these kinds of outcomes. All right. So just to sum up, extreme heat is occurring more frequently. For what it's worth, and I'm making a forecast here, you know, with the recognition, you know, we don't have a huge amount of skill. This summer looks like it's going to be on the hot side. That's what the climate models are showing. Our trends are that. And so anyway, remember you heard it here first. But there's no question in the observations, extreme heat is occurring more frequently. And what we're really seeing is more hot night events. And that obviously different groups are exposed to different amounts. And I would argue that some of the natural variability in the system gives us a chance to learn how to better adapt to these changes that are occurring and will continue. And that, you know, there's a lot of opportunities here for people to work in these kind of intersections between the, you know, what's the climate, the kind of health perspectives and so forth to kind of address this problem. And so with that, thanks. And hopefully we have a little time to kind of talk about this stuff.
Yeah, thank you very much, Dr. Bond and Dr. Spector.